In this problem, the mass of the bar, let's call it as a block, is given as small m, and the mass of the wedge is given as capital M. The left inclined surface of the wedge makes an angle alpha with the horizontal. There is no friction between any two surfaces in this problem, and we are asked to find the acceleration of the wedge here. Now, let us first understand the motion of the wedge here, how it would actually move. Now, if I release the system from rest, because of the gravitational force acting on the block would actually move down, and it is constrained to move on the wedge, so it will definitely slide down on this surface. Now, because of that, the wedge will get a push to the right and then it will accelerate to the right. Now, we are asked to find the magnitude of this acceleration. Now, whenever we work on any Newton's laws of motion problems, I would suggest you go through a series of well-defined steps that would actually help you arrive at the answer correctly. Now, usually the step 1 would involve something known as constraint analysis. Okay, so what do I mean by constraint analysis? The objects, whenever you have two or more objects in a system, they're constrained to move. Okay, so there is a relation between the displacements of the objects in the system. So the velocities are also related, the accelerations are also related. So the first thing that we need to do is get a relation between the accelerations of the block and the wedge. Now, most of the times we can actually do this visually by looking at the problem. So like in this case, so if I imagine a vertical line here, and suppose I'm holding the block and then making sure that it does not move relative to the wedge, and I take this wedge and then move it to the right by 1 centimeter. So when I do that, I have 1 centimeter string slack to the right of the pulley. Okay, so this 1 centimeter string is now available for me to displace the block relative to the wedge. So we can easily see that if I don't want any slack, the block can actually go down by 1 centimeter, and then this 1 centimeter displacement is, keep in mind, relative to the wedge. Okay, I hope you're clear about this. So if the wedge displaces 1 centimeter to the right, the block would displace 1 centimeter down relative to the wedge on its inclined surface. So if the wedge has acceleration a to the right, the block will have acceleration a down the inclined surface of the wedge. So that's how we have actually related the accelerations here. Now another way to think about it is, if I look at the block and then say that with respect to a person standing on the ground, so let's say there is an observer standing on the ground. Now with respect to this observer, let's say the block has acceleration ax horizontally to the left and has acceleration ay in the vertically downward direction. Now if I happen to think about an observer standing on the wedge, okay, he would say that, okay, so relative to the observer, with respect to observer on the wedge, okay, with respect to observer on the wedge, he will notice the vertically downward acceleration as it is ay. Okay, But horizontally, he would say that okay, the wedge is moving with acceleration a to the right with respect to ground, and the block is moving with acceleration ax to the left, that is again with respect to ground. So what is the relative acceleration? A person, let's say, from the perspective of the wedge. Okay, so these guys, you can always imagine that there are observers, let's say, standing. Okay, and then the observer on the wedge says that the acceleration of the block to the left relative to the wedge would be ax plus a. Okay, because they are moving in the opposite direction. Now, if I complete this vector triangle, this net acceleration, okay, so which is represented by this pink arrow, this should have the magnitude of a. Now, obviously, this angle will be alpha because these accelerations are relative to the wedge. Okay. Now, we can write here that ay can be written as a into sine alpha, and similarly we can write ax plus a as a cos alpha. Okay, so this sort of completes the constraint analysis, and then we can use these equations later. Okay, so once you're done with the constraint analysis, the step 2 would be drawing the free body diagram for these two objects. Okay, so draw FBDs. Now again, whenever we draw a free body diagram for an object, sometimes there are two options. Okay, either you can draw relative to a ground observer who is at rest, or relative to an observer who is moving. So in this case, if you take this observer standing on the wedge, you can actually draw the free body diagram of the block relative to this observer standing on the wedge, because he is standing on something which is accelerating. The wedge is accelerating, so this observer is a non-inertial observer. Okay, so if you recall, whenever you are working with a non-inertial reference frame, you're supposed to apply something known as a pseudo force. Okay, so we will try to solve this problem both using pseudo force and without using the pseudo force. Okay, so at times using pseudo force is better. Okay, again, there are situations where not using pseudo force is also better. But anyway, we will try to use both the approaches here. Okay, so now let us look at the free body diagrams for each of these two objects. Okay, so here I have drawn the wedge here along with the pulley. So because the pulley is literally attached to the wedge, and moreover it is massless, it's a good idea to treat the pulley as an integral part of the wedge. So if any object, so in this case the string, when the string applies any force on the pulley, it is indirectly applying on the wedge. So it is better to treat it as an integral part of the wedge. So the string on the right side is going to apply force, let's call it as T. Okay, and the string is also connected to the block down the incline. So here we can say the tension force is also in this direction. Okay, so string or thread doesn't matter, so I think we just call it a string. Now the block is going to apply a normal force perpendicular to the surface of the inclined plane, so that is N. Okay, so here because there is no friction between any two surfaces, so that means there is no friction between this surface of the wedge and the ground, so there will not be any frictional force here. So in order to calculate friction force, we may have to worry about the normal reaction applied by the ground, but in this case because there is no friction, I'm not really worried about the normal reaction applied by the ground, so we can ignore that. Okay, so and then it is clear that the wedge is anyway going to move along the horizontal line, so we're not worried about the forces in the vertical direction. Okay, now the wedge has acceleration a to the right. So now let us resolve the forces into components along the horizontal lines. Okay, so let's look at the normal reaction coming from the block. So if I take a horizontal line here, so this angle is also alpha, so those are alternate angles. If I take this dashed line and the horizontal as the parallel lines, so and then this is 90 degrees, so this is clearly 90 minus alpha. Okay, so when I resolve the normal force horizontally, okay, so this force vector would be n into cos of 90 minus alpha, which is n sine alpha. And if I take this tension force which is acting along the incline, and again here I take horizontal line as well, so this angle is again clearly alpha. So if I resolve this along the horizontal line, I get t cos alpha. Okay, now the right direction is dominating clearly because the wedge is moving to the right. So I'm going to take right side as positive. So I get, if I apply Newton's second law. So that's our step 3 actually. So our step 3 is apply Newton's second law. So keep in mind step 1, 2 and 3 are very important. Okay, so step 3 is apply Newton's second law. So here tension to the right minus t cos alpha, and if I take the component of the normal reaction, it is also to the right, so that would be plus n sine alpha. Okay, so that's the net force acting on the wedge in the horizontal direction, so that would be mass into acceleration. Okay, so here I'm now drawing the free body diagram of the block. I have two options here. So either I can work with a ground frame or the wedge frame. So now first I'm going to go with the ground frame. Okay, so if a person standing on the ground is trying to analyze the motion of the block, okay, so he has to worry about the forces now. So one obvious force again is the gravitational force, so which is mg downwards. Okay, and the normal reaction coming from the wedge. Okay, and the string is applying tension T in the upward direction. Okay, now these are the forces that act on the block, and then we are assuming that the block has an acceleration ax to the left and ay in the downward direction. Okay, so now we will have to resolve the force components along the horizontal line as well as the vertical line. So if I draw a vertical line and a horizontal line, okay, so let's mark the angles here. So if this is alpha, so this is a corresponding angle, so this will be alpha, and then this is clearly 90, so this is 90 minus alpha. Now in the horizontal direction, so if I look at horizontally, okay, so when I apply the Newton's second law, I'm assuming that the block is moving to the left, so whatever components we have to the left are dominating. So if I resolve this component to the left direction, so I should get a vector which is n cos of 90 minus alpha, which is n cos of 90 minus alpha is sine alpha, so n sine alpha. And if I resolve the tension along the horizontal line, I'll get t cos alpha. Okay, so what do I have here? I have n sine alpha minus t cos alpha. This is equal to mass into acceleration. So we have applied Newton's second law along the horizontal line. Now let us do the same thing vertically. So vertically, obviously the block is going down. So mg is dominating. So we're going to take downward direction as positive. So I have mg. And then what forces do I have in the upward direction? So if I look at the tension, its vertical component is T sine alpha. I hope you're able to see this. Okay, so this is alpha. So vertical component would be T sine alpha. And similarly, if I take the vertical component of the normal reaction, so that is n sine of 90 minus alpha, which will be n cos alpha. So since it is in vertically upward direction, I'm just adding with the T sine alpha, which is like n cos alpha. Okay, so now here, if I take the vector sum of the forces along the vertical line, I have mg, and the forces pointing in the upward direction, I'm writing them down with a negative sign here. So I have T sine alpha minus n cos alpha, and that is equal to mass into acceleration. Okay, so now if I look at, I mean, we are after the acceleration of the wedge, and then after having applied Newton's second law, we have a bunch of equations. Now let us just quickly look at if these equations are sufficient enough to get the magnitude of acceleration. So how many equations do we have? I would actually club these constraint equations as one. So let's say I have equation 1 here, and then this is another equation 2, and we have this is the third equation, and this is the fourth equation. Now let's look at how many unknowns we have. Okay, so let's mark the unknowns here. Okay, so we don't know ay. Okay, so that's one unknown. Okay, so we don't know a, that's the another unknown. And then I think from here even ax is not known. Okay, so maybe I think the first set of equations we can maybe call, let's say, equation A and equation B maybe. Okay, so there are two equations. So this is A and this is B. So there we have three unknowns. Okay, and then if I look at the other equations, I think the tension is unknown and the normal reaction is unknown. Okay, so but overall I think if I take these as two equations, I think overall we have 5 equations and 5 unknowns. Yeah, so the final step, yeah, algebraically it is a little scary, but with patience I think we can actually solve these equations. But whatever we have done so far, if we do that carefully, then we have applied our conceptual understanding of Newton's laws of motion correctly. Okay, so if we don't do this correctly till step 3, however good we are at solving linear equations, that is anyway not going to help us. Okay, so till this point it is very, very important. So what I will do is we'll carefully solve these 5 equations and then try to get the answer. Okay, so here I have just brought these two equations down here. So the first thing I'm trying to do here is get the values of the normal reaction and the tension in terms of AX and AY here. So to get the value of the normal reaction, we need to eliminate the tension here. So what we can do here is, if I take this first equation, okay, so I'll multiply on either side by sine alpha. And if I take the second equation, I'll multiply either side by cos alpha. and I subtract these equations. So when I subtract these equations, you should observe that in the first equation I have minus t sine alpha cos alpha. In the second equation I'll have minus t sine alpha cos alpha, so they disappear, and then we end up with only normal reaction here. So what do I get from the first equation? I get n sine square alpha. From the second equation, because I'm subtracting, in the second equation I have minus n cos square alpha. So when I add them, I get n into sine square alpha plus cos square alpha. I'm sure you know this identity, so which is 1. So I simply have normal here. Okay, and then from the left hand side of the second equation, I get mg cos alpha. Since I'm subtracting, I get minus mg cos alpha. And the right hand side I have m ax sine alpha minus m ay into cos alpha. Okay, so now you would have guessed how to get the value of the tension. So here, okay, I have the same set of equations. Now the first equation is multiplied by cos alpha, the second equation is multiplied by sine alpha, and then if I add these equations once I multiply, you can easily see that in the first equation, since I have n sine alpha cos alpha, in the second equation I have n sine alpha cos alpha, so they disappear. So what do I get here? I get minus t cos square alpha, and then I have sine square alpha, so I'll just get minus t here. Okay, and then from the first equation on the left hand side I don't have anything. From the second equation I have mg sine alpha, and on the right hand side I'll get max cos alpha plus may sine alpha. Okay, so here I think we have the normal reaction as well as the tension. So let me write the normal reaction here. So I think the normal reaction here will be n is equal to this mg cos alpha. I can take it to the right hand side, mg cos alpha plus max sine alpha minus may cos alpha. And similarly the tension here would be mg sine alpha minus max cos alpha minus may sine alpha. Okay, so what I would do next is I have these relations between the acceleration of the block and the acceleration of the wedge. So I will substitute these equations in the expressions that we obtained for the normal reaction and the tension, and then write those normal and tension only in terms of the acceleration of the wedge, which is what we're really after. So let us see how we can do this. Okay, so here what I have done is I have just substituted ax and ay in terms of the acceleration of the wedge, and then I get this equation. So I suggest you pause the video and then make sure you understand how I obtained these two equations. And then after that, all we have to do is take the values of the normal and the tension and then substitute in this last equation, which we obtained from the free body diagram of the wedge. So let us carefully substitute these things here. Okay, so now if you look at it again, I suggest you pause the video because I went ahead and then substituted the values of the normal reaction and the tension in this equation right here. So I suggest again, so if you are not really comfortable with solving equations. I know, I mean, we need lots of patience here. So I suggest you pause the video and then make sure you understand the substitution part here. I went ahead and then substituted everything here. So now once we're done with that, so if you look at several terms on the left hand side, the good thing is a bunch of terms actually disappear. So let's say I take maybe if I take mg sine alpha, I guess it's not there anywhere. So if I take ma cos square alpha, so here, and I have ma sine square alpha, so I can actually combine them as just minus ma, so keep that in mind. And then I have let's say ma cos alpha, where else I might be getting, so let's see. So now let's look at mg sine alpha cos alpha and then mg sine alpha cos alpha. So I think these two we can cancel them out. Okay, so they're done. Then here if I take a look at this term and this term, okay, so I have, if I take ma cos alpha as common, so I can actually write ma cos alpha into sine square alpha plus cos square alpha. Sine square alpha plus cos square alpha is 1. So I think we just have ma cos alpha here. So I have another ma cos alpha here. I think if I combine these two, I get another ma cos alpha. So just keep that in mind. And then I have ma sine square alpha, another ma sine square alpha. So if you combine these two, you'll get another minus ma. And then if I take the other two terms, I think they are alike with plus and minus sign, so you can ignore them. Okay, so that's pretty neat, I guess. So now let's look at what is happening here. So here, if I look on the left hand side, I have mg sine alpha, and I have minus ma. I think we said we're getting that twice, so I'll write minus 2 ma, and then ma cos alpha is also appearing twice, so that's 2 ma cos alpha, and that's it on the left hand side. So on the right hand side we have capital M into a. So now if you send these terms with acceleration a to the right hand side, and maybe we can write them on the left hand side. So I take a common, and then I get capital M plus I'll take 2m as common, and then I get 1 minus cos alpha. This is equal to mg sine alpha. So finally the acceleration of the wedge is mg sine alpha divided by capital M plus 2m into 1 minus cos alpha. Okay, so I hope you enjoyed this part of the problem. I know, I mean, the important part again is to really make sure that you are not doing any mistake in steps 1, 2 and 3. So the step 4 is really solving equations. So let me put it here. Yeah, I think that's where we need to be careful. At times it can be a little scary. Okay, so solve linear equations. I'll just put equations here. Okay, so now that we have obtained the acceleration of the wedge, so what I will do now is in this part of the solution I have used, when I looked at the free body diagram of the block. Okay, so here I have let's say resolved the forces. I've written the forces and resolved them, everything with respect to the ground frame. So now let us see if we solve the same equation relative to the wedge, would actually simplify our effort. Okay, so let's understand what happens when we do that. Okay, so here I'm trying to look at the free body diagram of the block from the wedge frame. Okay, so now let us look at the usual forces first. So we have mg acting down vertically, and the normal force applied by the wedge, and the tension up the incline. Now here we have to keep in mind that because wedge is accelerating, okay, any observer sitting on the wedge is a non-inertial observer. So we'll have to apply a pseudo force with magnitude as mass of the block and the acceleration of the wedge, but in the opposite direction of the acceleration. So the pseudo force gets applied to the left. Okay, so the pseudo force magnitude is m into a. So that's the pseudo force. Okay, so now that completes the free body diagram. Now all we have to realize here is we don't have to look at the regular horizontal and vertical direction. So we can just restrict ourselves to a different direction. So one along the incline, and then the other one is perpendicular to the incline. So if I draw those lines, okay, so this is one line we are interested in, and the other is along the incline. Now in this case we will have to resolve the gravitational force and the pseudo force. So if I first resolve the gravitational force, so along the line perpendicular to the incline, so if this is alpha, I think this will be alpha. So we have here mg cos alpha, and I'm assuming by this time you guys are aware of this. And then I have down the incline, I have mg sin alpha. Okay, now let us resolve ma. So ma, so this angle right here is also alpha. So if I resolve down the incline, in addition to mg sin alpha, I'll get ma cos alpha. And perpendicular to the incline, we get ma sin alpha. So I hope you guys are okay here. Okay, now perpendicular to the incline. So if I look at perpendicular to the incline, the block has zero acceleration. So the net force should be zero. So that means the sum of the forces upwards, which is like n plus ma sin alpha. Oh, what is happening? Okay, so ma sin alpha. Okay, this is equal to mg cos alpha. Okay, now if I look at down the incline, we have already understood that with respect to the incline, the block has acceleration a downwards. Okay, so down the incline, the forces downwards are dominating. So I don't know what is happening to my pen here. I guess I'll have to check my settings again. Okay, anyway, so now what forces are down the incline? I have mg sin alpha and ma cos alpha, and upwards I have tension T minus T, and that is equal to mass into acceleration. Okay, so here the advantage here is we get the value of the normal reaction and the tension with considerably less effort compared to the previous approach. So what we can do is, I know I get the normal reaction from the first equation and the tension from the second equation. I can just substitute in the equation obtained from the free body diagram of the wedge, and after that I think we should get the same answer. Okay, so here what I did is I took this equation from the free body diagram of the wedge and then substituted the values of the tension and the normal. Again, I suggest you pause the video and then make sure you understand how I obtained this, let's say, expression or the equation. Now, here, if you look at this this equation, so mg sin alpha cos alpha, I guess that's cancels, and then on the left hand side we have mg sin alpha. Okay, so oh my god, what is happening? Okay. Okay, so mg sin alpha, and then whatever I have with a, I'm going to send it to the other side. If I look at ma sin square alpha and then ma cos square alpha, I guess what is happening, let me check. Okay, a little while ago I made some plus minus errors here. So carefully look at this equation again. I think I have corrected it now. Okay, so the right hand side, if I take expressions with a, I'll get ma cos alpha, this 2 ma cos alpha, so that's minus 2 ma cos alpha, and then I have ma sin square alpha and then ma cos square alpha, so that's ma. So we can have 2m, the right hand side I can have 2m into 1 minus cos alpha and plus capital Ma. Okay, so finally the acceleration of the wedge is mg. Okay, so mg sin alpha, I'm almost done. Okay, so mg sin alpha divided by capital M plus 2m into 1 minus cos alpha. Okay, so I know this is quite a lengthy solution, but I think this is really a good problem to understand the concepts of Newton's laws of motion. Okay, so again I'll repeat these 4 steps. The step 1 is the constraint analysis. Okay, so you're supposed to do this constraint analysis. Okay, so that is to relate the accelerations of the objects in the system. The step 2 is draw a correct free body diagram. Okay, and if you don't show the relevant forces, then I think the steps after that will not fetch you the correct result. So make sure you practice drawing the free body diagrams correctly and then carefully apply Newton's second law here. So I should say second law. So we are applying Newton's second law here, and the final fourth step is like whatever equations that you obtain, you need to solve those equations. Like I said, patience is the key when you solve those equations, but I think at times the equations are not that daunting, so you can easily solve them. But my advice is to look at steps 1, 2 and 3 carefully and make sure that you are not making any errors there. Okay, so I hope you enjoyed this problem. I'll see you next time.